Today's the final day of MIT IT, and Eric here has given me permission to present whatever I want. So I'm presenting ad hoc problems today, which is like basically problems without really any standardized algorithm that we've learned in the past few days, and I'll provide some intuition on how to solve two or three problems that I find very interesting. So the first problem is marking light bulbs. You are given a binary array S of length n, and you could perform the following operation on the array any amount of times. So you pick an index that's like between 2 and n minus 1, such that the the binary number on the left of the index and on the right of the index are different. And then you invert the number at the index. So you set s of I to 1 minus s of I. If it's like 0, it turns into 1. And if it's 1, it turns into 0. So is it possible to convert this binary string s to another binary string t with some operations? If so, what's the minimum number of operations? I'll give you guys a bit to like process this problem, and then I'll get into it.
So you're looking for an index where the one before and the one after
are different, and then you flip the one at the index. Okay, is everyone done reading the problem? So like the first step to solving these types of problems is to identify like what does this operation actually do? So the constraint is that the one before and the index before and the index after are different. So we could list out all the combinations. It would be like 0 and 1, or 1 before and 0 after. So a pretty like common way to think about these problems is instead of zeros and ones, you have like colors of like black and white. So there's like 4 possible binary strings that you're editing. So 001 becomes 011, 011 becomes 001, 100 becomes 110, and 110 becomes 011. Does anyone notice anything about these operations? Let's take a closer look at like two of these operations. The 100 becomes 110, and the 110 becoming 100. So imagine we start with like an array that's like 1 and then a bunch of zeros after. We could repeatedly apply the operation 100 becomes 110, and then it kind of just slowly extends the range of ones. And if you have the reverse operation, like the 110 becomes 100, it kind of slowly shrinks this range, which is what these operations kind of do. So like this is a different way you could think about the operation once you visualize it and try it out on a few cases. So yeah, what does this operation do? It takes the right border of a range of ones and it grows or shrinks it. And the remaining 2 cases where it's like 001 becomes 011, and 011 becomes 001, these remaining 2 cases are like the mirrors of the first case, where it's for the left index and the left border of the range instead of the right border of the range. The next thing in order to solve this problem is I'm going to introduce the idea of an invariant. So an invariant is a function that takes in the binary string and outputs something about the binary string that doesn't change when you apply the operation. So if S prime is a modified version of S, then f of S would be f of S prime for all possible S primes you get from some number of operations applied to S. We know that if f of S doesn't equal to f of t, where t is like the target binary string, we can't convert S to T with some operations because f of S stays the same when you apply the operation to S. But if f of S is equal to f of T, we might be able to convert S to T. This remains to be proven, but as a general rule of thumb, if you find like some invariance, it will lead you closer to the answer. Does anyone like see any invariances in this problem?
The number of patches we have.
Yeah, the number of patches, precisely. The number of patches we have is an invariant in this problem because like you can consider the intervals or patches of ones. So if you have like two patches, you could expand them towards each other with some operations. But once you reach this state where it's like 101, we can't apply the operation anymore because the index to the left of the index and to the right of the index are the same. So you can't actually merge two intervals or patches together. This is an invalid operation. Does anyone see any other invariance? There's one more. But yeah, another case like that might change the number of patches is if you could shrink a patch until it disappears, but you notice that if you shrink a patch until it's like size 1, you can't actually remove it because the left and the right side of the patches are the same. They're both like zeros. So this is an invariant, but there's a second invariant that we need to solve this problem. Since the operation affects only indices 2 to n minus 1, the first number in the binary string and the last number of the binary string are also invariant. So now that we have identified these two invariants, if they are preserved from S to T, do you guys think it's solvable? Notice that we're basically like just the operations just grow and shrink the patches. So you're trying to like convert some amount of patches in S to some patches in T. It turns out it is solvable because like you could assign each interval to like a target interval because you never change the order of the intervals because they can't like merge into each other or anything. And then you just slowly move like the borders of the interval from the original place to like the target place. And that's how you solve this problem. Does anyone have any questions?
Wait, the ones that both ends can be touched, right? Because they won't have an index. They'll be missing one index on one side of it, right? The ones at the borders, left and right.
When the left and right borders, if you try to like merge them together, you get like the string ones, the substring 101, right? And then the left side is 1, the right side is 1. So because they're equal to each other, you can't actually apply the operation on that index.
Yeah, I was thinking about like index 0 of the whole array in the last.
But yeah, you can't apply the operation to index 1 or index n. I'm using one index here, but if you use 0 index, it would be just you can't apply the operation to index 0 and index n minus 1. It's just stated in the problem statement. So that's why those two indices are also invariants. So the number of operations would be like you just identify the border of the original range in S, which is like L and R, the left border and the right border. And then you have a target border, which is like L prime and R prime. And then the number of operations will just be the absolute value of L minus L prime plus the absolute value of R minus R prime, because every operation just moves the location of the border by 1. So you need this many borders to convert like LR to L prime and R prime. And let's do a bit of live coding for this problem. So this problem is marking light bulbs on Codeforces. The input here is the number of test cases. Then you have an integer n, and then a binary string s and a binary string t. I have already put the input here for convenience. But yeah, this is how you would identify how to input the input into the problem. So instead of like looking at the left and right ranges of the border, it is often convenient to just like view them as like the same, because there's the number of borders stays the same from S to T. So you could just match every border to a target border and not really worry about like which patch it is like a border to. So what we do is, the first of all, we should identify the invariant that if S0 doesn't equal to T0, or the last element is not equal, then it's just not possible. So we print -1 and we return. Otherwise, the case is that we have to check like the number of patches there are. But instead of checking the number of patches there are, we could also just check the number of borders of patches there are for convenience. So let's store a list of the borders of S and the borders of T. We iterate through every element in the range from like 0 to n-1, because a border has to be between two numbers, I and I+1. So if S of I doesn't equal to S of I+1, we know this is a border in S, so we just append this S borders. And same thing with T. And then we just have to check if the number of borders is the same instead of the number of patches. So if S borders, if the length of S borders doesn't equal to the length of T borders, we can't really create a border out of nowhere, so we just print -1 and return. Otherwise, we have a running total of the answer, and we just go through every border and see how much we have to move this border. And you just print the answer, and this should work. Let's see if it works. Let's copy the input in. And then we run the code. Oh, we have to define these variables. Wait, this is wrong. Let's see. Why is this? Wait, Eric, do you see any bugs? Huh.
Wait again, how are you defining the border?
Oh, the borders is like the left border and the right border of like each like patch or range of ones. But yeah, a substring of like the binary string where all of them are ones. And like the left side of the patch would be a zero, the right side of the patch would be a zero, or the border of the array. Let's see. So here we have one border, two borders, three borders. Here we have one border, two border, three borders. So let's print the size of S borders and T borders. It says the number of T borders is one. Wait, no, that's weird.
So it's like failing the first.
I think it's failing at the first print statement here.
Wait, can you strip your inputs? Input dot strip.
Like this. Oh, is there white space? Oh yeah, there was white space here. That's why. I see. So now we have the right answers. I guess there was just a bit of white space after something.
I think it includes the new one.
Oh, it includes the new line. So now we can submit. And we would choose PyPy because it's like faster than Python for some reason. And sometimes you have to read it. Oh, and it's accepted. Okay, so next problem's a bit harder. I think there's like a Codeforces problem similar to this, which is rated 3000. For context, the max rating is like 3500, but I find the solution of this problem to be really interesting. So the problem is that you're given a permutation of the numbers 1 through n, and then you could perform the following operation some amount of times. You pick an index I, and then you take the possibly empty prefix to the left of I and the possibly empty suffix to the right of I, and you swap the two subarrays. And what is the minimum number of operations to sort the array? It is guaranteed that you could always sort this array with this operation because like there is some proof involving the solution. So I'll give you guys a moment to read this problem. Like basically here, the yellow subarray on the left and the red subarray on the right are getting swapped with this operation. Oh yeah, this is using one index. Most like Codeforces problems use one index.
Because how would that work? Like you're at the very beginning, you choose that index.
If you choose the first index, it just moves like the entire suffix of the array to the beginning, and it moves like nothing to the end. So it basically moves the index to the end. It's like a cyclic shift if you know what cyclic arrays are. So an observation is that like the relative order of elements in the subarray stay the same. So like if you have one to the left of two in the yellow subarray, it's still going to be to the left of two when you switch it with the red subarray. But is there like a way to make the relative order of everything in the two subarrays stay the same? So the key idea to this problem is you turn the array into a cyclic array. So if you see the subarray on the left here, you have 1, 2, the index 3, 4, and then we add a border element x just to mark that that's like where we cut the cyclic array if we want to go back to the original array. So if you look at the left side, you have like 1, 2, I, 3, 4, X, which corresponds to the array on the bottom. And this split is like where you would cut in order to return to the original array. And on the right is like the cyclic array after you apply the operation. So does anyone notice anything about these cyclic arrays? Yes, that's the key. So we could actually rotate the cyclic array on the right to make it look like the cyclic array on the left. And then what happens is X and I are swapped. So instead of swapping two subarrays, now we're just swapping two elements, the index I and like whatever border element we have. This like massively simplifies the problem, and it converts a problem similar to something that is somewhat like standard in competitive programming, which is the subproblem of like what is the minimum number of swaps to sort a permutation. So like there's a link for geeks, but the key idea for this subproblem is you consider the graphical representation of the permutation where the index I maps to P of I. And then you look at what happens to this graph when you perform some swaps. So what this graph is called is a functional graph because every node has like one node it's mapping to and exactly one node that maps to it because it's a permutation. And it forms a bunch of little cycles. But what happens to these cycles when you swap two elements in the array? So the first case is if you swap two elements in the array that come from different cycles. For example, the second element and the third element of the array are in different cycles because 2 and 3 are in different cycles. So what happens is these two cycles actually merge into a single cycle. And this like visualization of 5 elements in the permutation might not be very intuitive. So I made a second visualization, which is like you look at the two cycles and then you're basically swapping where two arrows point to so that it forms like one giant cycle.
Can you go back to the previous slide?
Sure.
So how are these cycles made? Like, how do we know that 1 and 2 form a cycle? Is it just because they're relatively next to each other?
Oh, the cycle the graph is formed by like the permutation where like the index I maps to P of I. So if P is like here, P is 2, 1, 5, 3, 4. So the index 1 maps to the first element in P, which is 2. And that's how you form the graphical representation of a permutation. And there's a second case where like you swap two elements in a same cycle. And this what happens is it actually splits the cycle into two separate cycles, which is like the opposite of the merging cycle operation. And the visualization is that you're taking like two elements that some node point to, and then you swap them so it kind of slices the cycle in half. So when is the array sorted? When there are n cycles and each element is a self cycle, then that means this array is sorted because notice every element maps to itself because index 1 is supposed to be 1, index 2 is supposed to be 2, and so on. And let's introduce a new concept called a monovariant. It's similar to an invariant, but like it could actually change, so it's not invariant. It's like the number of cycles when you apply a swap operation, it can only increase and decrease by 1 every operation. So we know that we also know that if we increase the number of cycles to n, we solve the problem. So we know that the minimum number of swaps we need is at least like n minus the number of cycles we have because every swap can only add one cycle. And this is known as a monovariant because we're like monotonically increasing the number of cycles every swap. So let's go back to the original problem. The key difference between this like subproblem and the original problem is that we aren't able to just like swap any two elements. We could only swap elements in the cyclic array with like with the border element. So what happens when every swap requires this border element? There's this idea to swap like, if you want to swap indices I and j, you could swap I with the border element and then j with the border element. But this might not be optimal. There's like no proof that this is optimal. So we might want to go back to the graphical representation of the permutation in order to find something that's a little better. So let's analyze the structure. With a single swap, we can either merge two cycles or we could split a cycle in two, like we previously talked about in the permutation sorting. So we want to turn this array into many self cycles. So if the border element is a self cycle, we must swap the border element with something because that's what the operation does. So you would merge the self cycle of the border element with like some other cycle. Merging the border element with the self cycle would be counterproductive because we would probably just split that cycle in half with the next operation. So yeah, we probably want to merge with a cycle that isn't a self cycle. And the other case is the border element is in a cycle, but we could cut the cycle into two little cycles by just like, in this example, we have the border element maps to 2, 2 maps to 1. We swap these two mappings, so then the border element maps to 1 and 2 maps to itself. So we're basically breaking off a little self cycle from the big cycle that the border element is in. And so how many swaps do we need if we keep doing this? Well, for every cycle, we can only split it up into self cycles by merging it with the border element, because the border element is the only element that can be swapped with some element in the cycle. So if we have like k cycles that aren't self cycles and we want to split up these cycles, we must run the merge operation at least k times, because we need to merge them with the border element in order to like do something to their cycles. And what this does is this decreases the number of cycles by k, because each merge operation decreases the number of cycles. And after this, for every operation, after we merge like everything with the border element, we could just keep running the split operation and increase the number of cycles by 1 every time, because we just like split off the element that what we do is we swapped the border element with the element that maps to the border element. So this breaks off that element that maps to the border element as its own self cycle, and then it keeps everything else as a big cycle. And wait, no, we swap the border element with the element that the border element maps to, sorry. That would be how we break off an element. And we keep like the border element in the big cycle. So because the border element is in like the big cycle of all the non-self cycles merged together, we could just keep breaking off self cycles one by one. And every split operation increases the number of cycles by 1. And we want to like reach n cycles again, n self cycles, to get the array sorted. So let's say we start with like m cycles, k of which are like non-self cycles that are like separate from the border element x. We need to run the k merge operations to get all of these elements, all of these like non-self cycles connected to x, so you could run some split operations. And then we end up with like m minus k cycles after these operations, because every merge operation decreases the number of cycles by 1. And then now after we run these merge operations, we want to get to n self cycles by running the split operation. So since each operation increases the number of cycles by 1, we need n minus how many cycles there were after the merge operations. That amount of split operations is what we need to do in order to reach n self cycles. So the total number of swaps we need to do, or the total number of operations we need to do, is n minus m plus 2k. Does anyone have any questions on?
Non-self separate.
Non-self cycles that are separate from the border element. So they don't contain the border element in the cycle. Because if it's a self cycle, you don't need to merge it with the border element because it's already a self cycle. And if the cycle contains the border element, you don't need to merge it either because it's already merged with the border element.
Isn't there just one cycle that contains the border element?
Oh yeah, but we do have to take into account this one cycle. So that's what this separate means. Sorry for the bad wording, but there's like one final small detail in order to actually solve this problem. We are operating swaps on a circular array, but like any rotation of the circular array is still sorted if you have like bordered element to the left of 1, to the left of 2, to the left of 3, and so on. So we need to consider like, how do we index this circular array? Well, because the problem is pretty lenient with n is less than like 1,000 or something, we could actually just try every indexing and then run the permutation swapping algorithm in order to solve this problem. So does anyone have any questions? So yeah. And lastly, I'm gonna present a third problem, which is a more graphical problem. Oh,
How do you know that's like the best way to do it, or like how it's all basically?
oh, this?
Yeah.
Well, do you agree that we need at least k merge operations? Because, okay, after we do the k merge operations, we have n minus k cycles, right? And we know every swap operation can only increase the number of cycles by 1. And we want to increase the number of cycles by 1 after every operation because you want to reach n cycles. So running the split operation n minus m minus k times would be optimal. Does that make sense? The idea is that like the k-merge operations is needed because for cycles that are like not self cycles and separate from x, you do need to merge them with x in order to do anything to the cycle, because x is the only element that can be swapped. And then after that, you just run the normal permutation sorting algorithm. And so the last problem is acute path. So given n distinct points where n is less than 1,000, find a way to visit the points such that no formed angle is obtuse. So like this left side is good because it forms an acute angle. The right side is bad because it forms an obtuse angle. So for example, if you start from this green dot and then you go there, you can form an acute angle, another acute angle, and another acute angle. So this is a valid like path through the dots. But if you go from the rightmost green dot to this green dot to this red dot, this is not allowed because you're forming an obtuse angle. So does this problem statement make sense to everyone? Yeah. So I'll give you guys 5 minutes of thinking time for this problem actually, and try to find like a simple strategy that visits every element in this graph with only acute angles. Does anyone have any ideas? Doesn't have to be like proven correct or anything. Just like a heuristic.
I guess maybe a heuristic would be when you're at a node, like start pointing in a direction where you came from, or because that would start at like 0 degrees.
I see, but
and
what
then, like,
about?
open up?
Mhm.
I don't know how you would check that. It's an idea.
I think the problem with that is like if you start from a node, you don't really know where to go after that. Because there's no node that pointed from the starting node. Or do you just pick a red?
No, I was more saying like you went from like node 1 to node 2. Now start thinking about node 1,
Mm-hmm.
pointing back towards node 1, and then like
Mhm.
pointing outwards.
But what if you only have 3 nodes, like node 1, node 2, and node 3, forming like this obtuse angle, and node 1 just selects node 2? Because node 1 doesn't have anything pointing into it. Does anyone else have ideas?
Maybe go to the node that's the furthest away, then the node that's nearest home, the furthest away, the nearest. So I don't know.
That's actually really close. So the actual optimal strategy is you just go to the node that's the farthest away. And the reason why this works is you could prove by contradiction, actually. Like consider, so this is an example of running the algorithm, but consider like an obtuse angle. You form an obtuse angle if you like don't go to the node that's the farthest away. But like whenever you form an obtuse angle, you could actually just skip that angle and go to the node that's farther away. If that makes sense. Like if in an obtuse triangle, the longest side is opposite of the obtuse angle. So assuming that we do make an obtuse angle, our strategy isn't followed. So yeah. That's about it for today. Sorry that it's kind of a shorter lecture, but
Wait, can I just ask you like how you have an intuition? Like,
I know I see that if you went very far, if you are and then very close, then I don't know, like yeah, kind of like that, right? I know.
right.
You get it, and
The problem with going very far and very close is like if you have 4 nodes that are kind of in the shape of like this, you might go like very far and then very close and then back here. But the
Yeah.
intuition for going for the farthest node is you just take a look at an obtuse angle and you're like, how do I not form the obtuse angle? Oh yeah, we could just go to the farthest one. And then go backwards. Does anyone else have any questions? Okay, that's about it for this class. So just a quick reminder is if you want to pass this class, get credit for it, you need to solve 10 problems on VJudge due on the 17th. So if you haven't already, please create an account on the VJudge. And if you don't want to solve 10 problems, but you don't want to fail the class, you could also just like drop the class. Yeah, thank you all for your time. Thanks for coming to all these lectures. Here's like the credits of everyone who presented something in MIT IT, and the slides and recordings are at mitit.org/class. And finally, oh, and if you want more algorithm classes, the recommended classes are 1210, 1220, 5210 if you're a masochist, because that's like the graduate algorithms class and it's like really hard or something. And 18404. I think 18404 is pretty interesting advanced class that goes over like P and NP and stuff. Or you could just solve problems on your own on like MIT IT, Codeforces, @coder, or usecode.guide, or any other website like Dmoj, or VJudge, where we host a lot of our problems. Finally, we have the raffles.